Hello, welcome back. We've been talking about triple integration, um, in which we're talking about finding the integral of a function that's defined in 3 dimensions. So again, keep in mind we have maybe a room that has some temperature throughout the room. You are trying to maybe add up the total amount of heat in the room. Or maybe you have a balloon that has some charge throughout, and you're trying to figure out how much charge there is on the whole balloon. So you have this 3-dimensional object, and you're trying to add up a whole bunch of little bits of some function defined over that object. In the last video, we talked about what happens when our region is a box, but the region doesn't have to be a box. The region that we integrate over can be something super wacky, right? Whoa, this is my region that I want to integrate over. Um, well, in this class, we're not going to integrate over a region that's too crazy. What we're going to do is we're going to integrate over regions that can be defined as being between two surfaces. All right, so the reason why we do this is because it will allow us to take the triple integral that we need to do and convert it into a double integral. Now, the double integral might be a complicated uh, integral to do, but uh, at least now we're in the double integral land, and that makes our life a little bit easier. All right, so here are the three. Here's what this could look like. So let's say we have some region that is defined kind of like a cookie here. All right, we have some function u of xy, some other function, so that's u2, and here's u1 of xy. And the thing about these functions is that if we take our region and we project it down onto the xz plane, we get this a domain in 2 dimensions, and we would say that the region that we're integrating over is everything in that region D that lies between the lower function and the upper function. All right, so if you've been looking at my background during classes, you'd see uh, I have this picture. This is the same idea about taking a region, projecting it down onto the plane, and then there's 3 different ways in which we can do this. All right, so this is one way. If we project down onto the screen, then we can take our triple integral and we can integrate it over our domain. A little bit of function times volume is going to instead be a function times some z value times the function. So we've taken this triple integral and we've now written it as a double integral over a single integral that you do first. This is what happens if you project down into the xy plane and you get a nice representation for the region. You might also project over into the yz plane. So what does that look like? Okay, so this is x, this is y, and this is z. And so what we're saying is maybe there's some domain in the yz plane where you've got some lower function, u1 of yz, and you have some upper function, u2 of yz, and the region that you want to integrate over lies between those 2 functions. So take your region, if you project it down into the YZ plane, and you can represent it as a lower function as an upper function, then you can take this triple integral and reduce it to a double integral after you take that initial integral. One more example, right? So we've projected into the xy plane, or we've projected into the yz plane. We could also project into the xz plane. Right, so let's say there's some domain here that we have a nice representation for, and then we have some lower function here. This is u1 of xz, and we have some upper function u2 of xz, and your region lies between them. So in this situation, we would project onto the xz plane. We would first do the integral of f xyz with respect to y, and by doing that, we now we reduce everything to a two-dimensional, a double integral. All right, let's talk about what that ends up looking like. So the hard part here, of course, is going to be figuring out the bounds of your integrals. You have this three-dimensional object, and you need to figure out, well, what are the lower bounds, what are the upper bounds? So how do we do this? So we take our region, and we project it into the xy plane, the yz plane, or the xz plane, and look at this projection to find your domain D. After you find this domain, so you've taken your three-dimensional object, you've squished it, and now you need to unsquish it. You need some upper function and lower function. So just like in 2 dimensions, when we have this, maybe a picture that looks like this, we end up projecting down into the x-axis, and we say the x-axis, then we look at what the lower function is and what the upper function is. Well, this is the same idea, except now our projection is some shape, and we need to know what the lower function is, and we need to know what the upper function is. So after you've projected down into your domain, which in the past has been an interval, then we need to go up and figure out what that lower function is, what the upper function is. That gives the bounds on that innermost integral. Depending on the region, you might need to try a couple of different directions. And then you have to use all the tools in your toolbox to be able to integrate. So that may be going into polar coordinates. That may be the right way to do this. So in the next video, I will go through this example. Don't want to make this video too long. All right, so see you shortly.